Hey everyone, welcome back to Trigonometry. This is going to be lecture 3 of the course. And in this section we're going to do some examples of computing the values of trig functions of acute angles. And so we've talked through right triangle trigonometry, and we're comfortable with that. And so that in itself is enough to allow us to calculate the values of trig functions for any arbitrary acute angle. And so we're going to do some examples, and then we'll also take a look at a very common kind of applied problem that we'll see that trigonometry can benefit. So let's take a look at this. So we're going to start by calculating the value of the trig functions when the angle of interest is theta equals pi over 4. So we'll begin with the angle theta equals pi over 4. This is also known as 45 degrees. Okay. So our goal is to figure out what all of the trig function values are at pi over 4. Now, we haven't done anything like this yet. Previous examples, we were always given maybe one or more of the trig function values, and we were able to derive the remainders. But here we're starting from scratch with no values to work from, no triangle to work from, simply an angle. Okay, and so here's how this one would work. So we're going to consider a triangle. Okay, and the triangle I'm going to draw is this one. Okay, so you've got, it's obviously a right triangle, and these angles are 45 degrees. Now we know if this angle is 45 degrees, then that one must be also, because they sum to 90 degrees. Okay, and then I'm going to make the two sides equal to 1. So these will have the same length. And then this hypotenuse is unknown. We need to figure out what this hypotenuse is. Okay, so what is the value of C? Well, we can figure that out using the Pythagorean theorem. So what is the value of C? All right, well, we know that a squared plus b squared equals c squared. And so that means 1 squared plus 1 squared equals c squared. Okay, and so that means c is equal to the square root of 1 plus 1, which is just the square root of 2. Okay, so this guy here is the square root of 2. And so let's redraw it down here where we can reference it. 45 degrees, 45 degrees, 90 degrees, 1, 1, and the square root of 2. Okay. All right, and so once we've got the triangle that we want, once we know that this is a triangle, we've got 1 on both of the legs are 1, and the square root of 2 is the hypotenuse. Well, then we know that we can easily just apply right triangle trigonometry to figure out what all of the trig functions are. So the sine of 45 degrees is equal to the opposite over the hypotenuse, and so that's 1 over the square root of 2. And if you rationalize that, you get square root of 2 over 2. The cosine of 45 degrees is the adjacent side over the hypotenuse. And so it doesn't matter which one you use, but I'm using this one. So adjacent is 1 over the square root of 2. And so again, square root of 2 over 2. Okay, so we've got the sine, we've got the cosine. The tangent of 45 degrees is opposite over adjacent, and so that is 1 over 1, and so the tangent is 1 at 45 degrees. Now going into the alternative, the reciprocals, the cotangent is the easiest one to do. It's just also going to be 1 over the reciprocal of 1 is just 1. The cosecant of 45 degrees, well, it's the inverse, it's the reciprocal of sine, so it's hypotenuse over opposite, and that is square root of 2 over 1, so just the square root of 2 there. And then finally the secant of 45 degrees, that's the hypotenuse over adjacent, so that's the flip side of cosine. And so that one is also square root of 2 over 1. So just the square root of 2. So there we go. Right? And so we've used just basic right triangle trigonometry to figure out all of the values of the trig functions at theta equals pi over 4 or 45 degrees. Okay? And so as you can see, kind of the trick here is to be able to generate this triangle, a triangle that has the right length legs, basically, right? And has obviously the angle of interest in it. Okay. Now, once we know exact values, we can do more interesting kinds of problems. So, for example, we can do things like find the exact value of the sine of 45 degrees times the tangent of 45 degrees. Well, I mean, we know that we just found these values, didn't we? So the sine of 45 degrees is square root of 2 over 2. The tangent of 45 degrees is 1. And so this product is just square root of 2 over 2. Okay. What about an example like this, where we say find the exact value of, and this time let's make it cosine of pi over 4 minus tangent of pi over 4 plus sine of pi over 4. Okay. So here, again, we have all of these values. We just have to plug them in. So the cosine of pi over 4, remember that's just 45 degrees. We can just look back to the previous page and we see that the cosine there is the square root of 2 over 2. The tangent of pi over 4, 45 degrees, is 1. And the sine of pi over 4 is also square root of 2 over 2. Right, and so now we just need to add these numbers up. And we can do that pretty easily. This is, let's get a common denominator of 2. So I've got the square root of 2 over 2 minus, and now I'll make this 2 over 2. Instead of 1, just write 2 over 2. And then plus the square root of 2 over 2. Right, so I've got, what do I have? Square root of 2 plus square root of 2 minus 2 all over 2. And so this is 2 times the square root of 2 minus 2 over 2 equals, and I could do some factoring here, can't I? I can factor out the square, I can factor out the 2, sorry, and you get square root of 2 minus 1 over 2, and so this is just the square root of 2 minus 1. That would be the exact value, the exact value. And you could go through and you could go through and figure out what an approximate value would be, but this is the exact value. Okay. All right, so next we want to do the same kind of exercise, but now we're interested in different angles. So next let's find the value of the 6 trig functions at theta equals pi over 6, which is 30 degrees, and also alpha equals pi over 3, which is 60 degrees. So 30 degrees and 60 degrees. Now we're going to do this one together. We're going to do these two angles together, and I think you'll see as we kind of unfold the construction why that is. So we're going to start with a 30-60 triangle. Okay, so if I have a triangle, and I'll try to draw it reasonable, like something like this. So I've got a 90-degree angle here, and I've got a 60-degree angle here, and a 30-degree angle up top. Now we know that this works, right, because 60 and 30 makes 90, and so those are complementary angles, and this is the 90 degrees, so the whole thing is 180, so we have a valid triangle. Okay, and so let's say this is A, and this is B, and then let's set C equal to 2. Okay, so we're going to begin with this triangle. Okay, so we're going to begin with this triangle. Now what we're going to do is we're going to actually, you can think of it as kind of taking this triangle and spinning it, kind of doubling the size of it. We're going to rotate it around this B leg and kind of double, and we're going to double the size of the thing. Okay, so try to draw it here. Reasonable. Reasonable is okay. As long as it's reasonable, it'll be good for our purposes. So remember, we have C equals 2 here. This is B, and then we haven't figured out what A is yet, or B. So we just don't know what those sides are. If C is equal to 2, it's not obvious what A and B are without a little more effort, right? And so the little more effort that we're going to do is we're going to double the size of this thing like this. We're going to, you can think of just, again, just taking this and rotating it. So this is 60 degrees here, and this side up here is also 30 degrees. Okay, and so when I do that, I get a triangle that has 60 degrees here, 60 degrees here, and 60 degrees here. So think of it as this triangle, in case it isn't clear. 60, 60, 60. Like if you take the two sides and you think of it as all just one big triangle, then it's a 60, 60, 60 triangle, isn't it? Now this is a special triangle. It's called an equilateral triangle. Right? An equilateral triangle is a triangle where all of the angles are the same, namely 60 degrees, and as a consequence, all three sides of the triangle must be the same length as well. Right? So that means that this side over here is also equal to 2, and this side over here, this whole length here, is, sorry, this will be B. Well, I'm just going to write 2. I don't want to label them. So this side here would be 2, and then this whole side, which is A, and then this other part that's equal to A, is also equal to 2. Right? Equilateral triangle means all three sides are equal to 2, all three angles are equal to 60. Well, the sides can vary. I mean, you could shrink it up or expand it, but in this case, since we've called this side 2, then the other sides are going to be 2 as well. Okay. All right, so hopefully everyone's with me still. And so given this, we can do some, and basically what this allows us to do is to identify the length of A. This allows us to identify the length of side A. Now, in the original triangle, if the hypotenuse is 2, it's not obvious or automatic what A needs to be, right? But after going through this exercise, we do in fact see that A needs to be half of 2, so A is 1. Oh, A is equal to half of 2, so it's 1. So 2 over 2, right? Okay, that's good. So now we know C and we know A, and so we can use the Pythagorean theorem to find B. Let me recast what we know here before we go further. Okay, so I've got this triangle, and I've said that's 60 degrees. Here's the right angle. This is 30 degrees. Now I said C is equal to 2. This side is B. And through our previous argument, we said if C is 2 and this is a 30-60 triangle, then A must be equal to 1. Okay, so that's exactly what we needed. So once we have 2 of the 3 sides of a right triangle, we can easily find the third using the Pythagorean theorem. So A squared plus B squared equals C squared. Right, this time we need B. So I'll do a little algebra here, and I can see that B squared will be equal to C squared minus A squared. And B will be equal to the square root of C squared minus A squared. Right, and so what are those values? Well, C is 2, so 2 squared, and A is 1, so 1 squared. And so what do I get here? I get 4 minus 1, I'll write it, and so the square root of 3. Right, that's just the Pythagorean theorem, and so this guy here must be equal to the square root of 3. All right, so now I know all three sides of the triangle. I can use right triangle trigonometry to identify all of the values of the trig functions. We'll start with 60, so we'll start with this angle, and just know we're also talking about pi over 3, but I'm just going to use the degree notation. So this is sine of 60 will be opposite over hypotenuse. And so if this is our angle of interest, the opposite side is b, so it'd be the square root of 3 over 2. Okay. The cosine of 60 degrees is adjacent over hypotenuse, and so that's 1 over 2. And the tangent of 60 degrees is opposite over adjacent, and so that is square root of 3 over 1, also known as just the square root of 3. Okay, so those three can be pulled off of this triangle really quickly. And the others, cosecant of 60, well, we know that's just the 1 over the sine, so it'd be like 2 over the square root of 3, which is 2 square root of 3 over 3. Okay, the secant of 60, that's going to be hypotenuse over adjacent, or 2 over 1. So I'll just put 2. And then the cotangent of 60 degrees, that is equal to adjacent over opposite, or 1 over the square root of 3. Better way to write that would be to rationalize the denominator and write that as the square root of 3 over 3. Okay, so here's the 6 values for the angle of 60 degrees. All right, very good. We could do the same thing for theta equals 30 degrees. And so I'll just do that down below. I'll just write them out, and then you can confirm on your own that they are pulled from the triangle above. So the sine of 30 degrees, the cosine of 30 degrees, the tangent of 30 degrees. The sine of 30 degrees is 1/2. The cosine is square root of 3 over 2. And the tangent is square root of 3 over 3. And then, again, just pulling them from the triangle above, well, let me double check to make sure that that's good here. So sine of 30 degrees, I'm using opposite over hypotenuse there. Now 30 degrees here, the angle of interest is this guy. And so the opposite side is 1, the hypotenuse is 2, so 1 over 2, 1/2. All right, so that's how I'm doing it. All right, and I'll do the cosine as well, just to make sure. This would be the adjacent side over the hypotenuse. Right, and so in this triangle, the adjacent side is here, so it's square root of 3, and the hypotenuse is 2, so square root of 3 over 2. And you see that's what we've got here. All right, and then opposite over adjacent, opposite over adjacent would be 1 over square root of 3, otherwise known as square root of 3 over 3 after you rationalize it. Okay, and so then the cosecant is just going to be 1 over sine, so it would be 2. The secant is going to be 2 over the square root of 3, otherwise known as 2 square root of 3 over 3. And then the cotangent is 3 over the square root of 3, which would be 3 square root of 3 over 3. Okay, otherwise known as just the square root of 3, I guess. Okay, so now you've got the 6 trig functions for theta equals 30 degrees. Okay. Now again, both of these just came from this triangle right here, this 30, 60, 90 triangle, right? The quote-unquote hard part of this argument is just figuring out what the lengths of the sides of the triangle should be, right? And so what we did was we set c equal to 2, and then we used an argument from the equilateral triangle to figure out that a is equal to 1. So if c is 2, a is 1, and then using Pythagoras, we determined that b is equal to the square root of 3. And so once we have this triangle right here, then the rest of the problem is very straightforward. You're just going to look at the triangle, grab the opposite and the hypotenuse, grab the adjacent and the hypotenuse, the opposite and the adjacent, and just kind of go through and identify the different sides and pin them to these functions. Okay? All right. So that's fairly straightforward, hopefully. Let's do a couple of examples using these values. These are kind of straightforward. What is the exact value of sine of 45 degrees times the cosine of 30 degrees? Well, again, just kind of looking up above, we saw that the sine of 45 degrees was the square root of 2 over 2. And the cosine of 30 degrees, we just found it, it's square root of 3 over 2. Okay, and so we can multiply these together and we get the square root of 6 over 4. Okay. Another example, what if we want to find the exact value of the tangent of pi over 6, but we want to square the function, plus the sine of pi over 4, and we want to square that function. Well, again, we can just look up above. We know that pi over 6 that's going to be 30 degrees, right? And so the tangent of pi over 6 is this guy, so square root of 3 over 3. And now you can see that it's squared, right? So we have to square the value. And then the sine of pi over 4, that's the sine of 45 degrees. And that one, if you recall, is square root of 2 over 2. Now you don't have to memorize these. You just look back a couple lines up and find the values that you're after. Okay, and so we've got these values now. And so we can square each of these ratios. And we've got 3 over 9. So square root of 3 squared is 3. And then 3 squared is 9. And then we can square this one, and square root of 2 squared is just 2. And then just 2 squared is 4. So this is a third plus a half. Right, can we add those? Yep, 2 plus 3 over 6. And we have 5 sixths. 5 sixths. All right. Excellent. Okay. What I want to do next, and this will only take a moment or two, is I want to introduce the unit circle, and I'm calling it a reference sheet. Okay, you'll want to use this reference sheet as we go forward. And as we start to introduce more and more values and angles and concepts, the reference sheet will be more valuable. But we can start talking about it now. Okay, and so this is the unit circle cheat sheet or reference sheet, however you want to think about it. And so the way this works, we haven't talked about the unit circle yet, so just think of this as a nice, just think of this as a way to depict the angles. Right, and so the way it works is you've got 0 down here, and then pi over 6, that's a 30-degree angle, that's this green line here. Okay, and then pi over 4 is this line up here, this red one, that's a 45-degree angle. And then you've got pi over 3 up here, pi over 3, and that's your 60-degree angle. Okay, we'll get into all the rest of these later. But for now, we're just interested in this upper quadrant here. Now, so again, you've got the angle denoted here in radians, and then you've got the angle also denoted here in degrees. So whichever one you prefer, you can use. Now, the ordered pairs, as you can see, it says here cosine, sine. Right? And so you see these ordered pairs, like right here, for example, square root of 3 over 2, comma, 1/2. So the first value in the ordered pair is going to be the cosine. And the second value in the ordered pair is the sine. Okay, and so what this is telling you is that the cosine of pi over 6 is the square root of 3 over 2. And the sine of pi over 6 is 1/2. right? And equivalently, you could say the cosine of 30 degrees is the square root of 3 over 2, and the sine of 30 degrees is 1/2. Okay, and we have also the tangent and cotangent listed on this cheat sheet. So you've got the tangent, which is the tangent of pi over 6, which would be square root of 3 over 3. Right, and then the cotangent would just be square root of 3. Now we don't have secant and cosecant on here, but you can figure those out pretty easily from sine and cosine. Okay, and so that's what this this cheat sheet's all about. It's all about just being able to look at this picture and, given an angle, be able to go and reference what the value is on the sheet. Right. As we go forward with trigonometry, we will need to be able to quickly reference exact values of trig functions at key angles repeatedly, and we'll have to be able to do it quickly without having to crank up a bunch of right triangles and do a lot of geometry. It's important at the beginning when you're learning, like what we did just now. It's important to learn how indeed you could figure out what the exact values are at these different angles. But once you've done it, I don't know that you want to rely on that method to solve problems. And so the cheat sheet comes in after the fact. And so we'll develop all of the rest of these angles as well as the course goes on. And a lot of them we're going to get at a very discounted rate given what we just figured out today. And so we'll introduce some new concepts called reference angles and coterminal angles, and those concepts will give us a lot of these others for free. So this is the unit circle cheat sheet. There's other things down at the bottom that you'll see on here. Some of the, like the definition of the actual trig functions are here. I guess that's it, actually. The definitions of the trig functions. But the main value here is going to be just reading off the exact values for given angles. Okay, all right. So that's the unit circle reference sheet. And the whole idea of a unit circle, we'll get into that later in the course, not quite yet. And when we do, we'll come back to the unit circle reference sheet and cast the whole structure of the thing in a new light. And it'll be helpful to have seen it before and to be kind of working with it. Okay, we've got one more example that I want to go through. Just kind of an applied example, relatively straightforward, but just want to give you some idea. If you go and look at your books, your trig books, you'll find lots and lots of examples of applied problems where trigonometry is useful. And I'm just going to give you a flavor for that with this one very simple problem, but useful to see. Just kind of get you thinking a little bit about how these can be used to model things. So here's the setup. Given a tower, I'm going to write it out first. Given a tower of unknown height, okay, you are standing 500 feet from the base of the tower, okay, you are standing 500 feet from the base of the tower, and your line of sight with the top of the tower is 60 degrees. What is the approximate height of the tower? What is the approximate height of the tower? All right, so let's draw a picture. So just to reread it, given a tower of unknown height, you are standing 500 feet from the base of the tower, and your line of sight with the top of the tower is 60 degrees. What is the approximate height of the tower? Right, so let's draw this picture. So I've got this tower here. Okay, so some kind of a tower. I suppose I could have put a little more into, maybe I'll write it like this. Yes, much better, right? Okay. All right, so it's a tower, okay, and we don't know how high it is. We don't know how high the tower is. Now, you, as the observer, are standing somewhere over here, and this is obviously not drawn to scale. So you're standing over here, and your distance from the base of the tower, we'll take that to mean the center of the base. Your distance from that base is 500 feet. All right. And so you're 500 feet from the base of the tower, and you're looking up. Maybe you've got an instrument or something, but you're looking up, and when you look up at the top of the tower, you can see, the very peak of the tower, and you've got some kind of an instrument that measures your line of sight, right? Maybe like a scoping device or some kind of you've seen these things. You'll see people out, and they're just looking through these little scopes, and it'll measure the angles here that's made with the floor, and you've got one of these kind of devices, and so you've determined that this angle is 60 degrees. Okay, so your line of sight angle is 60 degrees approximately. Okay, and so the question is, how high is this tower? What is the height of the tower? And so you can probably see just by looking at this, there's some kind of a triangle implied here, right? The implication is a triangle, right? And because it's a tower, there was a right angle implication here, right? And so just to refine this model, this is more like what the physical scenario would look like, but you can model this as just basically a right triangle with a 60-degree angle. So here's the right triangle, here's the 60-degree angle, that's where you're standing. This is your line of sight here, the hypotenuse. Right, and one leg is 500 feet, and the question is, what is this leg, h? Right, and so we can use a very simple trigonometric, this can be solved very simply just using basic trigonometry that we've learned. Right, and so which of the trig functions can we use to create an equation that includes this leg and this other leg? All right, so the hypotenuse is not important at this point. The two legs are what we're interested in. And so we know that the tangent can be used. Right, so specifically the tangent of this angle, 60 degrees, we know that that's equal to the opposite over the adjacent. Right, and in this case, the opposite side is the h, the height. Sorry, not the hypotenuse. It's the h that we're interested in, and the adjacent side is the 500 feet that we know. Right, like this. And so what I have here is I have an equation: tangent of 60 degrees is equal to h over 500. Okay, now I need to know what h is. How can I figure out what h is? Well, I can just do some algebra here, can't I? I can multiply both sides by 500. So I get 500 times the tangent of 60 degrees is equal to h, right? If I multiply this side by 500, they cancel. If I multiply this side by 500, I get 500 tan 60. Okay, and so that means that h is equal to 500 times the tangent of 60 degrees, and we know what the tangent of 60 degrees is. We just figured it out. It is square root of 3. Right, so the square root of 3. And if I pull out a calculator and I multiply 500 times the square root of 3, I'm going to get something approximately 866. 866 feet. And so this is telling me that the tower, if I'm standing 500 feet away and I got to crane my neck 60 degrees to see the top of this tower, then the height of the tower is approximately, I'll put approximately 866 feet. Okay, so this is just a simple application of trigonometry. And there are many, many examples where just a right triangle can model the problem, and just basic trigonometry will allow you to get pretty good answers. So, all right, we're going to leave it there for this section, and we will see you all in the next lecture, where we will just continue onwards and upwards. Okay, take care.